So guys, let's talk about one more result and then move on to something known as scalar triple product. So the result is, as we were watching some results related to areas and areas of triangles and parallelograms, this is one more result. What does it say? Let's see. It is saying that the perpendicular distance of small c vector. So what is this? You're going to figure it out. The perpendicular distance of c vector from line joining a vector and b vector is. So basically what this is trying to say is that in your plane or in your space, wherever a and b, there is a line joining a vector and b vector, and there is a point c vector. What is the perpendicular distance of c vector from the line joining a vector and b vector? Basically these vectors are nothing but position vectors. Instead of saying find the perpendicular distance of a point C from the line joining point A and B, alternative fashion to say the exact same thing is find the perpendicular distance of the position vector of say point C given by C vector from the line joining the position vectors of A and B points, which are small a vector and small b vector. So basically let's find this out. Suppose this is my point C whose position vector is C vector. Its perpendicular distance I need to find from the line joining say a vector, which is nothing but the position vector of point A, and b vector, which is the position vector of point B. Now obviously one thing which is intuitively pointing towards this is to form a triangle ABC. When you form this triangle ABC, you are free to use any concept related to triangle in here, because now the question just wants the height. I want the length of CM. So what will this be? So once we have considered this to be a triangle, I have many approaches to follow through this particular result. First of all, area. Area of triangle ABC. It will be what? If you remember, we have done that when you have a triangle whose vertices are given to you as position vectors, a vector, b vector and c vector, then how do you compute the area of the triangle? We have done that. It is given by half of mod of a vector cross b vector plus b vector cross c vector plus c vector cross a vector. This is a vector, this is a vector, this is a vector. Sum of three vectors is a vector. Magnitude of that is a non-negative real number. Half of that is again a non-negative real number, which is my area. But if I go by the conventional format of finding the area, that is area of the same triangle ABC is half into base is BC, into height is CM, or rather what I can write this as, BC is what? What is this BC? Or over here it is actually AB, not BC. This side is AB, which is standing to be the base of this triangle. So what is this side AB? If I consider it as vector AB, if I consider this as vector AB, in that case, length of the line segment AB is the magnitude of vector AB. So instead of AB, I can write magnitude of vector AB into CM. What is AB vector? Well, you know that AB vector is position vector of B minus position vector of A. Position vector of point B is small b vector. Position vector of A is small a vector. And therefore, at this particular point of time, I can write this as half of magnitude of B vector minus A vector into Cm. Now, please keep on understanding, I am using the vector terminologies here, but B vector minus A vector is a vector. Its magnitude is giving me a non-negative real number. Cm is actually the length of the line segment Cm. So, again non-negative, half is again non-negative. So, this is continuing to be a non-negative real number. Don't confuse these terminologies when they are written with this particular entire expression being a vector quantity. No, it is a scalar quantity, that too non-negative. Now, this is my, I should say, second equation, and this is first, because both of them are giving me the area of the exact same triangle ABC. So, now I can say by 1 and 2, because both the equations are giving me the area of the same triangle, I can equate both of them. In fact, they will be equal, and therefore, obviously because one triangle cannot have two areas, so I have half of mod of A vector cross B vector plus B vector cross C vector plus C vector cross A vector is equal to half of mod of B vector minus A vector cross Cm. Don't forget what you need to find. You actually need to find Cm. What is Cm? Cm is the perpendicular distance of C vector from line joining A vector and B vector. I need to find this. So, basically Cm is what I need to find. Now, if these two are equal to each other, you can very easily see this half and half cancels out, and therefore Cm comes out to be what? Cm is nothing but magnitude of A cross B plus B cross C plus C cross A whole upon magnitude of B minus A. Non-negative, non-negative, division of two non-negative is again non-negative. You get the length of the line segment Cm as this. So, we just found the area of the same triangle by two different approaches, wherein we were using the position vectors of the vertices of the triangle and then equated both the areas and then got the answer as this. Okay? This result, once understood and kept in mind, leads us to the next topic of study, which already, as I told you, is scalar triple product. Now, we have understood about dot product, which is also called scalar product, and that dot product was basically for two vectors, right? Now, we have to move on to three vectors and understand what is scalar triple product. What is scalar triple product? See, it is dot product, but not only dot product. It is scalar product, as I am saying, but not only scalar product. What it is? See, till now we are through with understanding dot product of two vectors, that it is a scalar quantity. Then we moved on to understanding cross product of two vectors, which was a vector quantity. And now we are moving on to understanding scalar product of three vectors, which again would be a scalar quantity. Why and how? Let's see. I am saying let A vector B vector, C vector. So clearly I told you it's triple product, so I will be taking 3 vectors and not 2. Let A, B, C be 3 vectors. Then if A, B, C are 3 vectors, then scalar triple product, then the scalar triple product of A, B, C denoted by, so first of all you need 3 vectors to talk about scalar triple product. So this line makes complete sense that you want to talk about scalar triple product of these 3 vectors A, B and C. This is denoted by this A, B, C and then again closed bracket. So the moment you find this written anywhere, it is actually denoting the scalar triple product of these 3 vectors. Now, scalar triple product of ABC denoted by this is defined as a scalar quantity given by, so see, this is the order in which this is written, first A, then B, then C. Here order matters. We are going to do properties of scalar triple product where this is going to make complete sense to you. Right now A is the first, B is the second and C is the third vector. So this particular scalar triple product of these 3 vectors in this order is given by what? So scalar triple product of these 3 vectors in this order only is given by A vector cross B vector, A vector cross B vector, this is a vector, cross product of 2 vectors is a vector, dot C vector. So A cross B is 1 vector, C vector is 1 vector. I am talking about dot product of these 2 vectors. At the max, what you can do is, let me tell you, A cross B is not equal to B cross A, so you cannot swap A and B with each other. Here if you carefully see, dot product is commutative, so at the max what you can do is write this. So this C vector can come over here or over here. These expressions actually are exactly the same. You have 2 vectors with you and you are taking dot product of them. So as I was saying, this is a vector, this is already a vector, and when you take dot product of 2 vectors, what you get is a scalar. And that is why scalar triple product of 3 vectors A, B and C is a scalar quantity, because it is defined in this fashion. So always remember, scalar triple product of A, B, C with A first, B second, C third can be written as A cross B whole dot C. A cross B whole dot C. This is how you need to remember and understand that this is actually coming out to be a scalar quantity. That is why it's called scalar triple product. Fine. If it would have been coming out to be a vector quantity, which we are going to do after this article, which is vector triple product, that is what the name is, because the answer comes out to be in that case a vector quantity and not a scalar quantity. Now, when we were doing dot product of 2 vectors, cross product of 2 vectors, we understood the geometrical applications of both of them. So it's obviously our duty to understand the geometric application of even the scalar triple product. And that in itself is very exciting. Let's move ahead with the geometric interpretation of scalar triple product. Now this is something really exciting, and moreover, let me just give you this small signal that because we are involving 3 vectors, we will be moving a dimension higher, And now the thing will not be about planes, it will actually be about spaces. So we are going to work on 3D figures now because we have involved 3 vectors. Till the time we had 2 vectors, we were working with planes, whether it is dot product, whether it is cross product. And now we'll move a notch higher, a dimension higher, and work in the 3-dimensional planes as you have 3 vectors with you. So let's begin this interpretation, which is geometric, of the scalar triple product. I'm saying let A vector, B vector, C vector be 3 adjacent sides of a parallelopiped. Now what is a parallelopiped? I'll just show you. Let ABC be 3 adjacent sides of a parallelopiped given by OA vector, OB vector and OC vector. So let's see. Basically, if you have, say, this point is O, this point is O, this is your OA vector, say this is your OB vector, and say this is your OC vector. So I'm saying this is my point A, that's point B, and that's point C, and this is O. Complete the parallelopiped. Basically, these are adjacent sides of a parallelopiped. So you need to complete the entire parallelopiped. So let's complete this parallelopiped. If these are adjacent sides of parallelopiped, how would you be completing this parallelopiped? Here there will be a more slant because we basically have the base of this parallelopiped as a parallelogram. So once you are through with this, you will be ending up watching a parallelopiped. This is a parallelopiped. Basically, the base is a parallelogram, upper base is a parallelogram. It's basically made up of 6 parallelograms. So this is a parallelopiped, as I was saying. This is my point B. This is A vector. This is B vector, and this is C vector. Now, what you need to do over here is, if you just understand this particular base of this parallelopiped, I would actually be moving ahead with the scalar triple product with these 3 vectors as the adjacent sides of this parallelopiped. Now, if you remember the cross product, what was the thing about cross product? See, first always remember that when I am talking about A cross B dot C, this is what is the scalar triple product of A, B and C. So scalar triple product is actually dealing with cross also and dot also. First let's talk about cross. What is A cross B? A cross B. Now when I am talking about A cross B, I am only focusing upon this plane which is of A cross B. So I am talking about this. Right? A cross B deals with this plane. Why? Because this is actually a parallelogram, and I can say A cross B is actually equal to, if you remember the geometrical interpretation of the cross product, A cross B was equal to what? The magnitude of A cross B vector. What was A cross B? A cross B was a vector whose magnitude was equal to the area of the parallelogram with adjacent sides as A vector and B vector, and the direction was perpendicular to the plane in which this parallelogram is kept. So I can say magnitude, which is area of the parallelogram, area of this parallelogram. So if this is A, this is B, this is O, so suppose this is this is say D. I have OBDA. Multiplied by unit vector in the direction perpendicular to the plane containing this parallelogram. So unit vector in that direction, let me mark it as this perpendicular. Okay, this is a perpendicular to this particular plane and it has the name as n cap. So this is the direction which is perpendicular to the direction of the plane containing this parallelogram or plane of this parallelogram, and unit vector in this direction is what is denoting my n cap. So area of the parallelogram OBDA times n cap was what? The geometric interpretation of the cross product of A and B, right? If this is the scenario over here, what do you think will be A cross B dot C vector? What will be A cross B dot C? It is area of parallelogram OBDA times n cap. This is one vector. Dot product with C vector. Now let me remind you of something. What is this? This is a scalar quantity. Area of the parallelogram is a scalar quantity, that too non-negative. So if I am taking this scalar to be suppose m times n cap dot C vector. Now n cap is also a vector, C vector is a vector. If you remember, we have done this property. I can write this as this, or I can write this as this. So I would actually be choosing to write it like this. And so because this is just a scalar, I can keep it outside. I am going to get area of parallelogram OBDA times n cap dot C vector. Now for dot product, I need the angle between n cap and C vector. Suppose this angle that you can see between n cap and C vector is suppose angle phi. So this small angle that you can see is suppose phi. In that case, what is n cap dot C vector? Now see, what is this parallelogram OADB? This is actually the base of this parallelopiped. So I can say area of base of the parallelopiped times what? N cap dot C vector. What is A dot B? Mod A mod B cos theta. This is mod of n cap mod of C vector cos phi, where phi is the angle between n cap and C vector. So I have marked that. Now you can very clearly see what is mod of n cap. N cap is a unit vector, so mod of n cap is 1. So you get again area of base of parallelopiped and here you have this is 1, so you have mod of C vector cos phi. But over here, if you drop a perpendicular, from point C to this vector n cap, you are going to obtain a triangle OC, and suppose this point, let me rub this from here, suppose this point is G, this vector is n cap, suppose this point is G, then when I drop a perpendicular from C to this particular vector or this direction, I get a triangle which is CGO. And what is the case with this triangle? Let's understand. So in triangle OGC, if I talk about cos phi, it is what? Now this is the right angle. So cos phi will be, this is the base OG upon OC. Fine, OG upon OC. What is OG? This is OG. And what is OC? What is OC? OC is actually the magnitude of vector C. So I can write this as OC times cos phi, or OG is equal to not OC but magnitude of C vector times cos phi. So over here you have got magnitude of C vector times cos phi. I will be replacing this by OG. So therefore what I get is this particular term, which was coming out to be equal to this, is further coming out to be equal to something else. That is what? Therefore A cross B dot C is equal to area of base of the parallelopiped times OG. What is OG? If you can very clearly see, this was a perpendicular drawn to this plane, right? This is perpendicular, and what is OG? OG is actually the height of this parallelopiped, isn't it? OG is the height of this parallelopiped, and therefore I can say area of base of the parallelopiped times the height of the same parallelopiped. So what is this? Area of the base of the parallelopiped multiplied by the height gives you just nothing but the volume of the parallelopiped with adjacent sides, as you can see in the figure, as A vector, B vector and C vector. And what is this equal to this? And what is this? Scalar triple product of A, B and C. So scalar triple product of A, B and C is coming out to be nothing but the volume of the parallelopiped with adjacent sides to be A, B and C. And that is what is the geometric interpretation of scalar triple product. In this case, we have moved a dimension higher and considered a 3D figure, and therefore we are not getting area anymore, we are getting the volume as the answer of the geometric interpretation of scalar triple product. So over here, instead of this notation, you also famously use this notation as I just told you, and therefore this comes out to be equal to the volume of the parallelopiped with adjacent sides to be these three vectors whose scalar triple product in this order you wish to find. Now that we are through with this particular geometric interpretation of scalar triple product of three vectors, let's talk about certain properties of scalar triple product. First thing that is very interesting and useful related to the property of scalar triple product is that if the three vectors are cyclically permuted, if the three vectors whose scalar triple product you want to find are cyclically permuted, then the value of scalar triple product does not change. The value does not change. What do you mean by this? If they are cyclically permuted, see, say this is A, this is B, this is C. Cyclically means this order should not be disturbed of ABC. The cycle should not be disturbed. You can begin from anywhere, but don't disrupt this cycle. If you begin with A, your cycle will be ABC. If you begin with B, your cycle will be BCA. If you begin with C, your cycle will be CAB. But don't disrupt the order. Okay? Begin from anywhere, but don't disrupt the order. So this is saying that scalar product of A, B, C, scalar triple product of these three vectors in this order is same as scalar triple product of BCA, which is same as scalar triple product of CAB. So basically what this is trying to say is that A vector cross B vector dot C vector is equal to B vector cross C vector dot A vector is equal to C vector cross A vector dot B vector. So what this is in a way trying to tell you is that you can interchange the dot and the cross sign provided the cyclic order is not disturbed. So A cross B dot C can be written as B cross C dot A, can be written as C cross A dot B. All these are going to give you the exact same results. But what if you disrupt the cyclic order of these three vectors? What if you disrupt the cyclic order of these three vectors? So there comes the next property. If we change the cyclic order of vectors, then the scalar triple product changes in sign but not in magnitude. So magnitude remains the same, but the sign changes. What do I mean by this? Let me tell you. Scalar triple product in this order. In this order, the scalar triple product of ABC is denoted by this. What you do is, suppose let me not put an equal to sign here. If you are not writing BCA, rather writing BAC, suppose. Or here if I say, let A be the same, here I am writing this. Now ACB is not the cyclic order. See? ABC, this is the cyclic order, this is not the cyclic order ACB. So basically this particular scalar triple product will be negative of this. Or I should write, this will be equal to negative of ABC. Whenever you are interchanging two of them, interchanging any two of them, changing the order of any two of them, there is a minus sign which gets attached. So here this will be equal to, suppose you are interchanging these two. So this will be B, A, C. But minus of what it is. So minus of what it is plus only, right? So you are getting that ACB is actually minus of ABC, which is equal to BAC. I am just disrupting the order of any two. Any two you disrupt the order. Suppose these two you swap. C here, B here, and A is here. So this is negative. So these two are going to differ by a negative sign. That is it. You can disrupt the order, not a problem. If you are not disrupting the order, the cyclic order, nothing changes. Magnitude as well as sign remains the same. But when you disrupt the order of any two vectors in the cyclic triple product, what happens is the value changes by a minus sign. Magnitude remains the same. If this is 3, this comes as minus 3. So magnitude wise both are 3, but sign actually changes. So you can go on doing this. If you again disrupt the order of any two vectors, it will be minus of what it is, so it will become plus of that. So this happens to be our second property, again very useful. Working on with the next property, as I was telling you also, that the sign or the operation, you can say, of cross and dot can be interchanged if the cyclic order is not disturbed. What I am trying to say is, scalar triple product of this is A, this is B, this is C. What is this? A cross B dot C. You can change or swap these two, provided you are not disrupting the cyclic order. You can write this as A dot B cross C. Right? You can write this as A dot B cross C, which is what? B cross C dot A. Right? Dot product is commutative, and this is what? B, C, A. So this is kind of the first property itself. If you can see, the scalar triple product of ABC was same as scalar triple product of BCA. So I was explaining it there also, that I am just trying to interchange this cross and dot sign, and that can happen when I do not disturb the cyclic order of these three vectors. The property now that comes is really interesting. What is that? Let's see. So we have over here that the scalar triple product of any three vectors is 0 when any two are equal. So when any two vectors out of the three vectors are equal, we have the scalar triple product to be 0. Let's see. This is what you have as the definition. First thing, if A vector is equal to B vector, suppose A vector turns out to be equal to B vector, then this will be A vector cross A vector dot C vector. If you remember, we have recently done this, that A vector cross A vector is 0 vector, and 0 vector dot product with any vector gives you 0 only, scalar 0. Next, if A vector is equal to C vector, then this happens to be what? A cross B dot A vector. A cross B dot A vector. Now, if you know A cross B is perpendicular to A vector, I told you in the last lecture itself, I think. And therefore, if two vectors are perpendicular, their dot product is 0. Again, last case, if B vector is equal to C vector, then the scalar triple product of ABC, if B vector is equal to C vector, scalar triple product is A vector cross B vector dot B vector. I know A cross B is a vector which is perpendicular to both A and B. And therefore, their dot product will again be 0. So, this is a very important property, that if two vectors out of the three vectors are equal, definitely scalar triple product will be equal to the scalar 0. Still, there are many more properties to discuss. I'll see you in the next class. We'll discuss the same. Thank you.